Thank you so much, Chairman. Good afternoon, everybody, or late good morning or early good evening, depending on where you are on the geographical lens on this planet. So as you have heard already, I would like to review a little bit together with you the CRMs for testing of the presence absence of Staph aureus enterotoxin A, or in short SEA in cheese. A little bit setting the scene first. So these enterotoxins, unfortunately, are causative agents in food poisoning outbreaks. So you might see this in a newspaper or hear it on the news once in a while, that in a school canteen, university canteen, wedding, or a big party, that people are getting sick hours after ingesting a certain type of food. So you have the symptoms the poor guy on the right side shows. So you start vomiting a few hours after ingesting those toxins. You get diarrhea, you get fever. So it's not very nice. It's a little bit comparable to what you would undergo if you ingest Listeria or Campylobacter, so pathogens that are not made for us, let's put it like that. And we certainly don't want to have in the food, and the toxins neither. As you can see, as little as 6 nanogram of this toxin in a 100-gram food portion would already suffice to induce these negative effects in about 10% of the exposed populations. So that means we need a very sensitive method to, in order to make sure that we can reliably detect and be sure that a food does not contain the toxin. These toxins are proteins of between 22 and 28 kilodalton large. They are a problem in itself because they are highly stable to changing temperature. So temperature changes up to 50, 60 degrees are not affecting, let's say, the activity of those toxins. The same holds for a pH change, and they are also quite resistive to proteolytic digestion. Meanwhile, more than 30 serotypes of these toxins are known. Unfortunately, I have to say only 5 at the moment can be detected with commercially available detection kits. For the other 25, people are developing methods. Mainly these are ELISAs, so immunoenzymatic methods, which are very sensitive and selective, and more also LC-MS, working on multiplex methods to detect basically up to, I think that the latest paper was speaking about 25 different SEs in one method. And SEA was chosen in this material because it's the serotype most frequently involved in FPOs of the 5, I have to say. For the other 25, we are fishing a little bit in the dark. We have a Commission regulation from the year 2007 on microbiological criteria for foodstuffs. The toxins are a little bit exotic there because they are not microbiology. All the other criteria refer to the Staph aureus itself, or the Listeria, or the other pathogens. And this is the only one, if I remember correctly, which refers to products of the pathogens, namely these toxins. And the regulation addresses specifically cheeses, milk powders, and whey powders, and also gives basically the method that has to be employed for the testing. And this is the so-called European screening method of the EU reference laboratory for coagulous positive Staphylococci, which is located in Paris, in France. And this method was called in the old days detection of Staph enterotoxin type A to E in milk and milk products. And over the years, the method has been extended to many more types of foods like fish, meat, ready-to-eat foods, desserts, and finally in 2019, the updated ESM, now they speak about all types of food, while they map out a large type of food matrices, was converted into an ISO method and into an ISO standard called horizontal method for the immunoenzymatic detection of these toxins in foodstuffs. And interestingly, for a good reason, I would say, the method defines that the sample intake has to be 25 grams of a food. In our case, it's a cheese, so the cheese comes in wheels of a few kilos, and or the whey powder comes in bags of 50 kilos or 100 kilos. So you have to take 25 grams of this food, whatever the food might be, as a starting amount to start with the sample prep, and you have to do this 5 times in total. And in order to comply with the legislation, with the 2007-1441, in all 5 cases, the result has to be not detected in all cases. What does it mean, not detected? The regulation also specified a method, and the method basically works as follows. So first you have to prepare the sample. You take the 25 grams of your food, you add warm water, you mix the sample very, very harshly, usually with an ultra-thorax device, in order to make sure that you have a quantitative recovery of the toxin in your extract. You have to adjust the pH 2 times. You centrifuge the sample, and the supernatant is then subjected to dialysis concentration. That sounds a little bit odd. I had to look it up because when I did at the university dialysis, it was to basically during protein purification, you dilute the sample, you don't concentrate it. But what you do here is to submerge basically the dialysis tube, which contains the solution with or without toxin, in polyethylene glycol. And the pack basically pulls out the water and concentrates the sample. And once this is done, you then subject this concentrated supernatant to 2 commercially available detection assays or kits. One is the so-called WIDER Z2. The method principle is enzyme-linked fluorescence detection, and the other one is a very basic ELISA and is called RiderScreen Z Total. It's important to note that each of these assays, it's a multiplex assay, can detect toxins A, B, C, D, and E, or combinations thereof. So if you get a result which says toxin present, it means it could be one of those or a combination of those or all of those. So you cannot distinguish among the toxins, but it's not important because you want to have a screening method. So very important, and basically on this everything depends on the whole reference material and on the methods as well, is the threshold. The threshold between present and absent is correctly defined, and this basically was defined by the kit providers in an extensive validation study using many different matrices and different toxins at different concentration, with or without dialysis concentration. I'm not going into detail. And a result that you obtain below the threshold or cutoff called sometimes is interpreted as the toxin is not detected. If the result is at the threshold or above, then it would mean we have toxin in the sample. Then we had to decide which matrix do we choose. Cheese was already clear because this was a request from the EU laboratory. We opted for Tom de Savoie, which is a very nice raw milk cheese from France. Why did we do this? Because raw milk cheeses are not pasteurized, and as a real scenario, these types of materials are more prone to have this kind of contaminations, especially if the hygienic conditions are not very good. And then we also had to decide on the SEA concentration in the cheese. Do we go for 1 or 2? In the end, we decided basically the most important one should be close to the limit of detection of the assays in order to make it, let's say, competitive, because this is the most important, let's say, quantity region where the test needs to be done. We wanted to have what I call a strong positive, and of course also include a blank material. So for the processing, very briefly, we produced a set of 3 materials. The 359A was the blank. The B contained about 0.1 nanogram toxin per gram of cheese, and the C contained about 0.25. How do we know? We purchased commercially available SEA, checked the purity and identity of the SEA, prepared a solution, a spiking solution, and this was then quantified using amino acid analysis using isotope dilution mass spectrometry. Now for the processing itself, we removed the rind first of all, cut the cheese into small cubes. For the blank material, this were pre-ground before freeze drying, and then the obtained freeze-dried cake was then mixed in order to have a homogeneous powder. For the toxin-containing materials, after the pre-grinding, we added the water. We added water in order to prepare a slurry of cheese, which was then spiked with the SEA solution, mixed again, freeze-dried. The freeze-dried cake was again mixed, and then we had basically the A material, a powder, and a highly contaminated material that was then combined in the relative ratios so as to obtain the B and C concentrations, let's say. Final mixing, and then the materials were filled under inert gas into plastic sachets. So this is a representation of the processing. The cheese wheels, They weighed about 3 to 5 kilos, and we started with 300 kilograms of this cheese. So that was a few weeks of production time, cutting of the cheese into smaller cubes, pre-grinding, plating them out on freeze-drying trays and put them in the freeze dryer for the blank directly, or preparing a slurry, which was spiked. On the right-hand side in the second line, you see the freeze dryer from the outside. The cables are the probes in order to follow the freeze drying process. Finally, we had the powders that had to be mixed in different quantities. Then we see a representation of the filling on a filling device. And finally, the three materials next to each other were put in an aluminum pouch for protection. Homogeneity and stability. We have quantity data from the assays. I could also call it a sort of quantity, because what you get is a fluorescence signal, a value on a scale, on an artificial scale, or an absorbance units at a certain nanometer wavelength. But of course, you don't get a readout in the sense of nanogram toxin per gram of sample, but that was not important. We used those direct readouts for the evaluation of the homogeneity and stability, because we wanted to have more information than just saying a negative is a negative and a positive is a positive. And the uncertainties were calculated because we had the numbers, but we didn't use them in the end, as you will see soon, as we decided in the end to, instead of an uncertainty, to give a lower limit of confidence on the certificate. We did the homogeneity only for the B and C material. For the A, we tested the cheese that we purchased for the absence of SCA. For the B and C, we took 10 units from the prepared batches using a random stratified sampling scheme and analyzed 3 replicate independent analysis per unit. Using the Widers method, because the Widers is slightly better in performance in terms of repeatability compared to the other one. And all the 60 results, so 30 results for 2 materials, all of them were correct as expected, let's say. And additionally, also, I will come back to that in a second, all the results from the characterization study that we obtained were also correct. And this serves as an additional homogeneity check and assessment. We did our usual statistics for outliers. We used the Grubbs tests at 99% confidence level, no outliers, and there were also no trends using regression analysis at 95%. These are the numbers. The numbers are a little bit better for the C material, owing to the fact that the concentration of the toxin is higher. So the closer you get to the limit of detection, the larger the variability, which is normal. For the B material, we couldn't calculate what we normally do, the SBB, which is the between bottle variability, because the ANOVA that we employ gave us an MS between value, which is smaller than MS within, meaning that you cannot calculate SBB. And the U*BB, which is the second best option, let's say, to estimate an uncertainty contribution to a potential inhomogeneity, is the contribution that could be hidden by method repeatability is usually a little bit lower than the SBB, and the values are very, very meaningful and low and certainly fit for purpose. On the graphs, you see the representation of the filling sequences of the B and C material. You see as the arrow bars basically the SWB values from the ANOVA and the mean values of the 3 replicates. Continuing with the short-term stability, again, only done for the toxin-containing materials using the same assay. We tested it for 18 and 60 degrees with a reference temperature of -70. We employed a so-called isochronous study using 0, 1, 2, 4 weeks as the time points. Isochronous means you store your samples, different samples at different temperatures for different times. And once all these times are elapsed, you put them at reference temperature. Once all the samples are at reference temperature, you analyze them in one go, ideally under repeatability conditions to bring down the effect which comes from the method. Again, no outliers, no trends. The uncertainties were calculated but not used in the end. And these are the numbers in terms of short-term stability uncertainty expressed in % per week. So again, very reasonable, very low numbers. The graphs represent the B material tested at 18 degrees, so you don't see any trend visually. If you look at the 60 degrees, which are very harsh conditions already for the toxin-containing material C, you see a slight positive trend, but this is most likely a measurement artifact or could be a small sign of the matrix starting to degrade. But the trend was not statistically significant. Finally, the long-term stability, again, only for B and C with the widers. Here we choose fridge and freezer temperatures for testing, and the reference temperature again at -70. Isochronous study as for the short-term stability, this time 0, 4, 8, and 12 months. For the B, we had one statistical outlier that we kept. This is our internal policy at the JRC, that we are very conservative in removing outliers. We only do that if we find a clear technical reason. That was the case for C, where one of the sample was basically fully spilled during the sample prep, so we couldn't use it, and we didn't take the result into account. For the B, we had a significant trend at +4 degrees, but no trend at -20. When I looked at the data further, I could see that basically the statistical outlier caused the trend to happen. So if we would have removed this, the trend disappears. For the C, however, which is the identical material, just with a little bit more toxin, we don't have trends at these temperatures, meaning that everything is fine. Uncertainty were calculated and not used. The ULTS, so the long-term stability uncertainty in % per year, is again somewhat lower for the C material. Again, the graphs show basically that the long-term stability is guaranteed, and the little trend that you see on the left side is again not significant. We also included a 2-year study, but only took the time points 0 and 24 months into account, and I'm not going into details here. That's not that much important. I can conclude that basically the 2-year study confirmed the other stability data that we had, meaning the material is sufficiently stable. For the characterization, I prescribed that each lab that participated should analyze 3 independent samples per day with 3 analysis days, so 9 samples, so a 3 × 3 setup. The reconstitution basically relates back to the freeze drying. This is basically the loss of water that you have to reconstitute the cheese powder with water to basically start with a cheese sample of 25 grams. And the method was, of course, prescribed as the ESM with one of the 2 commercial assays. In the end, we had 8 data sets with the widers and 7 with the reader screen assay. Some individual data were excluded for technical reasons. So here I've been very strict. So if the reconstitution masses were not respected, the data was not taken into account, even if it was correct. The pH adjustments according to the method have to be made very thoroughly. So you have to titrate down to pH 4, if I'm not mistaken. And 4 means 3.8 to 4.2. If the pH drops too far or is not reaching 4.2, the sample will not be taken into consideration, or if the final mass of the concentrated sample was outside the prescribed range, again, was not taken into account. Finally, we could say that for the A material, we had 112 valid results, so all the individual results were reported as SEs not detected, whereas for B and C, we had 122 and 125 valid results respectively, meaning all those were reported as SE detected. A graphical representation now of the quantity values. I only show you one slide from widers data. So the upper one is the blank material. The green line is at 0.13 test value. So this is the arbitrary scale of this test. And the test value of 0.13 is the threshold basically. So everything above the threshold is positive, everything below the threshold is interpreted as negative. And as you can see, the 8 labs with the mean and their standard deviations are all far below the threshold, which indirectly proves also, this is not the purpose of this exercise, but indirectly proves that this assay apparently for this matrix toxin combination works very well, very discriminative. In contrast, the B material with the toxin, you see again the green line at 0.13, and you see the mean of the means of the laboratories around 1.1. So again, you are considerably above the threshold, and you conclude, yes, the SE toxin, SEA in this case, is present in the sample. Next one was then the value assignment. We had to somehow convert this information into a value And of course, there was the question, should we give a plus minus on a certificate? Should we put a word present absence? Is this helpful? Shouldn't we rather go for a, let's say, property which can be expressed quantitatively? And that was done in the end. So we opted to choose the diagnostic specificity for the A, which is defined as the true negatives divided by the sum of true negatives and false positives. In contrast, for the toxin-containing materials, this is then the diagnostic sensitivity defined as the true positives divided by the true positives plus false negatives. As we didn't have any false positive nor false negatives in all those analyses, the certified values down here are, of course, then 100%. And then the question was, how do we express the uncertainty? Can we express the uncertainty in the classical way? That was relatively soon clear that will not work, or it will not make a lot of sense. And then we decided to use a lower limit of confidence as a sort of one-sided confidence interval. And that was calculated according to this formula that can be found in the Matrella 1963 reference. And then we could calculate from the data that we had, you remember the 112, 122, 125 results, we could calculate this lower limit of confidence. So we can say that with a 95% limit, with a 95% confidence, the true value is somewhere between 100, which was the value that we obtained. But if we repeat the exercise, it could be that one or the other false result would be obtained. And so we are between, let's say, 97.5 and 100%. For the users, I think also very useful to get basically the quantity readout from the tests directly on the certificate that we did, but not as a certified value, only as an AMI, additional material information value. So this is the summary. You see that the VIDAS is a little bit more discriminatory for this kind of samples, for these Gs and for these chosen toxin concentrations. And we opted to give not only the mean value, so the mean of the laboratory means, but also the individual value in interval, with the lowest found in all the labs and the highest found in all the labs. Now, for the metrological traceability, of course, you have to follow this procedure very strictly. If you don't, the result might be different. So we could conclude that the properties are operationally defined, as we call this. The identity of the SCA was, of course, checked. We used STS page to see that we get a band at the mass where it should be. We also performed confirmatory ELISA, which specifically only detects SCA and nothing else. We could have done other analysis like LCMS of the intact protein, which we did in another project later on. Anyway, the identity was assessed beyond reasonable doubt, let's say. And all the input parameters that were used by the laboratory, so the balances, the pipettes and everything else, was properly calibrated to make sure that basically SI traceability can be reached. The consistency of the results from the study has also demonstrated that the input factors were properly covered. And as the assigned values are combinations of agreeing results that are individually traceable to the SI, the assigned value themselves are also traceable to the SI. That we could conclude. What do you use the CRMs for? Method validation if you want to set up the method in your laboratory, but more important even for method performance control. So if you do this test regularly, you want to check once in a while, and once in a while is not once a year, but more often, for sure, that the method performs as it should perform. I also want to mention that we used a similar approach much earlier in the mid and late 1990s. The first example is BCR 599 used in goat's curd. There we had two materials, goat's curd, I believe, 100%, and the other one was 99% goat's curd mixed with 1% used curd. So it's again a little bit like the meat materials Steve was describing. It's the authenticity reference materials. And there I looked up the certificate. The approach was not identical, but very similar. So we gave a certified value as the lower limit of confidence. So the certified value was then, for example, bigger than 98%, something like that. And the property was called back then probability of correct identifications, which is basically similar, not to say content-wise the same as sensitivity and specificity, and we also had the very first GMO reference material that was produced in 1997 or 98, which was dried soybean powder containing this Roundup Ready construct. And the properties on the certificate back then were called sensitivity, specificity, and in addition to these two, the efficiency was given of the two PCR methods that were employed to analyze the material. And with this, I want to conclude my presentation more or less by giving the most important references that you can consult if you want to have more information, especially the two publications where we describe in detail the feasibility study, where we investigated how can a commutable reference material be produced that mimics a real cheese sample as good as possible. The processing was described in detail, as well as homogeneity and stability. And the second one is more relating to the characterization approach. I would like to thank our processing team, formerly IRMM. IRMM was still alive and kicking in between 2013 and 16 when the material was produced and certified. The EU reference lab for CPS in Maison Salfort in Paris, in France, and of course the participating labs in the characterization study, and of course you for your attention. Many thanks, and I'm happy to take questions. Thank you.